So here is our equation of motion again. Phi dot is equal to mu minus sine phi, where phi is the difference in the phase angles of the swarm of fireflies and the one firefly who was trying to join the crowd. And mu is a measure of the coupling in the system. And so it's a difference of the angular speeds of the swarm and the single firefly divided by the coupling strength. Let's apply geometrical methods to understand the behavior of this equation of motion. So let's plot as a function of phi, let's plot phi dot. First, let's look at the case where mu is equal to 0. So then phi dot is just equal to minus sine phi. So this is a periodic function, like so. So here is pi, here is minus pi. And so this is the case where mu is equal to 0. And so there's a single stable fixed point at the origin. So here, phi star obviously is equal to 0. There's no phase difference between the swarm and the single firefly. And this happens when mu is equal to 0, which means that either the angular speeds of the firefly's swarm and the single firefly are identical, or the coupling is so strong, infinitely strong. So let's now look at a different case. Let's suppose that mu is positive. So for positive mu, all that happens is that we just shift the sine function slightly upwards. So here's the behavior for positive mu. And now we have two fixed points. There is a stable fixed point at some phi star, which is given by sine inverse of capital omega minus little omega over a. And then there's an unstable fixed point, which we're not going to worry about. But notice the behavior of this non-trivial fixed point. In this case, phi is positive, phi star is positive, which means that capital theta is larger than little theta, which means that there is a phase lag. So in this particular case, when mu is positive, that means that the speed of the swarm is faster than the natural speed of the firefly itself. So the firefly is always trying to catch up. And because it's trying to catch up, and what the manifestation of that in this model is that it lags behind in phase compared to the swarm itself. On the other hand, if mu is less than 0, then we have the opposite picture. Equation of motion looks like this. There is an unstable fixed point here and a stable fixed point here. So this is phi star, which is now less than 0. So the feature where there is either a phase lag or a phase advance, when mu is negative, that means that the speed of the swarm is slightly slower than the speed of the single firefly. And so the single firefly is always ahead of the pack and sort of being swallowed up by it. So it's a phase advance compared to the swarm itself. And clearly, this feature where there is either a phase advance or a phase lag, this occurs as long as our sine function with this shift intersects the horizontal axis. And so this feature is what's called entrainment, when the single firefly actually does attempt to synchronize with the swarm. And this entrainment clearly occurs only if mu, absolute value of mu, is less than 1. That's the only way that the sine function will go through the horizontal axis. And this is the same as minus 1 is less than omega minus omega over a, less than plus 1. Or omega is less than omega plus a, little omega plus a, or little omega minus a. So this gives us the precise condition under which in this idealized model entrainment can actually occur. If the angular frequency of the swarm is too far away from that of the original firefly, entrainment can't happen. And what we see by this equation is that entrainment happens when the angular frequency of the swarm lies close enough to that of the original firefly, and close enough is defined by the coupling constant a.